Welcome to Lecture 7 Linear Algebra. We're still on Section 1.3 Applications of Systems of Linear Equations, and today we would be looking at a couple of examples. Our text again is Elementary Linear Algebra by Ron Larson, 7th edition, Cengage Learning. This is Dr. Gilbert, Eyabi. Now let's review a few basic assumptions of network flow. The first is that the total flow into a network must equal the total flow out of the network. And secondly, the total flow into a junction in a network must equal the total flow out of the junction. And Kirchhoff's laws: all current flowing into a junction must flow out of it. Secondly, the sum of the products I times R, I for current and R for resistance, around a closed path is equal to the total voltage in the path. Now, example 1, network flow. Set up the system of linear equations to represent the network shown in figure 1.10, then solve the system, i.e. find x1, x2, x3, x4, and x5. Now we're going to go through this example very slowly and carefully, being our very first example. So, solution. We're going to start with junction 1. Recall that the total flow into a junction must equal the total flow out of the junction. So in junction 1, the flow into the junction is 20 and the flow out of the junction is x1 plus x2. So x1 plus x2 equals 20. Junction 1 done. Junction 2. The total flow out of the junction is 20 plus x3 and the total flow into the junction is x4. So we have x4 equals x3 plus 20. Junction 3. The total flow into junction 3 is x2 plus x3 and the total flow out of junction 3 is 10 plus 10, which is 20. So we have x2 plus x3 equals 20. Junction 4. The total flow into junction 4 is x1 plus 10 and the total flow out of junction 4 is x5. So we have x1 plus 10 equals x5. And in junction 5, the total flow into this junction is x5 plus 10, which equals the total flow out of the junction, which is x4. I call this my raw system. Now I would rearrange this to look like what we've seen before. So rearranging, we have x1 plus x2 equals 20 and so on and so forth, and this gives us our beautiful system that resembles what we've seen before. And setting up the augmented matrix using your iPad with the Math Studio app, we can do the reduced row echelon form of the matrix, and this right here is our RREF, the reduced row echelon form of the matrix. You can tell very quickly that the last row disappears, so that means we end up with infinitely many solutions. And solving as we did in previous lectures, we end up with x1 equals t minus 10, x2 equals minus t plus 30, x3 equals t minus 10, x4 equals t plus 10, x5 equals t. That is our free variable where t is a real number. Okay, example 2. Determine the currents I1, I2, I3, I4, I5, and I6 for the electrical network shown below. Let's start with junction 1. The currents flowing into junction 1 are I1 and I3, and the current flowing out of junction 1 is I2. Recall Kirchhoff's first law. All the current flowing into a junction must flow out of it. And the second law, the sum of the products IR around a closed path must be equal to the total voltage in that path. Okay, now let's go to junction 2. The currents flowing out of junction 2 are I1 and I4, and the current flowing into junction 2 is I2. Now let's look at path 1. Recall Kirchhoff's second law. The sum of the products IR around a closed path must be equal to the total voltage in that path. So in path 1, the products IR would be I1 times 2. So we have 2I1 plus 4I2, and that will be equal to 10. The sum of the products IR must be equal to the total voltage in the path. 2I1 plus 4I2 must be equal to 10. We repeat the same procedure for path 2, path 3, junctions 1, 2, 3, 4, and we end up with 7 equations. Okay, let's go on to the solution. We start first with Kirchhoff's first law. All the current flowing into the junction must flow out of it. So we have I1 plus I3 equals I2. Do the same thing for junction 2. I1 plus I4 equals I2. And we can repeat the same process or procedure for junctions 3 and 4. And we have this system of linear equations. Now, Kirchhoff's second law states that the sum of the products IR must be equal to the total voltage in the path. So for path 1, we have 2I1 plus 4I2 equals 10. Repeating the same procedure for path 2 and path 3, we end up with a system of 3 linear equations, and putting all of these together and rearranging like we did for the first example, we end up with a system of linear equations. 7 equations, 1, 2, 3, 4, 5, 6, 7. But the good news is that we only have 6 unknowns, I1 to I6. Now, setting up our augmented matrix, this is what we have, and we can solve this using our iPad, the Math Studio app. Do RREF, reduce row echelon form, and we end up with I1 equals 1, I2 equals 2, I3 equals 1, I4 equals 1, I5 equals 3, and I6 equals 2. And of course, current is measured in amps, so just make sure the units of measurement are put correctly in place. Okay? Are you ready for this? It's a very simple problem. Network analysis, water flow. Water is flowing through a network of pipes in thousands of cubic meters per hour, as shown in the figure. Your task is to solve this system for the water flow represented by x1, x2, x3, x4, x5, x6, and x7. Now, when you solve the system, I want you to go back and find the water flow. In other words, solve the entire system when x6 equals x7 equals 0. Again, go back to the system and do the same thing when x5 equals 1000 and x6 equals 0. Let's see what you come up with. Thank you.